Welcome to today's paper reading. Today's paper is titled, LongNet, Scaling Transformers to 1 Billion Tokens. This paper was published on AR14 by Jiayu and colleagues from Microsoft Research and Zheng University. LongNet is a novel transformer variant designed to scale sequence length to over 1 billion tokens without compromising performance on shorter sequences. The core innovation is dilated attention, which exponentially expands the attentive field as distances increase. This approach results in linear computation complexity and a logarithmic dependency between tokens. LongNet can serve as a distributed trainer for extremely long sequences and is a drop-in replacement for standard attention, integrating seamlessly with existing transformer optimizations. Experimental results show strong performance on both long sequence modeling and general language tasks, opening new possibilities for very long sequence modeling. Figure 1 illustrates the historical progression of sequence lengths in transformer models over time. The graph showcases the increasing capacity of models like GPT, sparse transformer, reformer, memorizing transformers, RMT, and LongNet. Notably, LongNet represents a significant leap by scaling sequence length to 1 billion tokens, demonstrating the advancements in handling longer sequences without compromising performance. This trend highlights the continuous efforts in enhancing the computational efficiency and expressivity of transformer models, paving the way for more comprehensive and complex language tasks. Scaling sequence length in neural networks offers significant advantages. It provides models with a large memory and receptive field, enabling them to interact more effectively with human and the world. Longer contexts also contain more complex causality and reasoning paths, which can be exploited during training to improve generalization. Additionally, it opens up the potential for in-context learning, which could be a paradigm shift for many-shot learning. However, this scaling presents challenges. Balancing computational complexity with model expressivity is crucial. Traditional RNN-style models, while effective, are limited by their sequential nature and lack of parallelization during training. Transformers, on the other hand, suffer from quadratic complexity and self-attention. To address these issues, the authors propose LongNet with dilated attention. This novel component achieves linear computation complexity and scales sequence length to 1 billion tokens, overcoming the limitations of previous methods. Figure 5 illustrates the runtime performance of our dilated attention mechanism compared to vanilla attention. Both methods are implemented using the flash attention kernel to optimize memory usage and speed. The key observation is that while vanilla attention exhibits a quadratic increase in runtime as the sequence length grows, our dilated attention scales linearly and maintains nearly constant latency. This demonstrates the efficiency of our approach in handling long sequences, which is crucial for scaling up to 1 billion tokens without significant performance degradation. Table 1 provides a comparison of the computation complexity among various methods. The recurrent method has a complexity of O and D squared, while the vanilla attention method has a higher complexity of O and squared D. In contrast, the dilated attention method, introduced in this work, achieves a significantly lower complexity of O and D. This table highlights the efficiency gains of the dilated attention method, which is a key component of the LongNet solution that scales sequence length to 1 billion tokens. Dilated attention in LongNet involves splitting the input into segments and sparsifying these segments by selecting rows at a specified interval. This approach significantly reduces the computational cost compared to traditional attention mechanisms. Additionally, a mixture of dilated attentions is employed, which combines different segment sizes and uses dynamic weights to effectively capture both long-range and short-range dependencies. Furthermore, multi-head dilated attention is implemented, where computations differ among heads by using an offset for sparsification, and the outputs of different heads are concatenated to form the final output. Figure 2 provides an overview of the dilated attention mechanism used in LongNet. This mechanism involves splitting the input into segments, and then sparsifying these segments by selecting rows at a specified interval. This process significantly reduces the computational cost compared to vanilla attention. The figure illustrates how this method models both short-range and long-range dependencies, with the number of attention patterns adaptable based on sequence length. Figure 3 illustrates the mechanism of dilated attention with multiple heads. The key feature is that the attention patterns vary among different heads by shifting their positions successively. Specifically, for the JTH head, an offset Sj is calculated as J modulo R when selecting the query key-value pairs. This offset ensures that each head processes a different segment of the input sequence. The outputs from all heads are then concatenated to form the final output, maintaining the same computational steps as in the single-head counterpart. This approach enhances the model's ability to capture diverse dependencies within the data. Figure 4 illustrates the distributed training process of LongNet on two GPU devices. The training is parallelized by partitioning the sequence dimension, ensuring that the computation and communication costs remain nearly constant as the number of devices increases. This approach allows the training to scale effectively to an arbitrary number of GPU devices, enhancing the efficiency and scalability of the LongNet model. The distributed training algorithm for LongNet involves splitting the input sequence along the sequence dimension and projecting it into queries, keys, and values on separate devices. For segment lengths within the local device's capacity, attention is computed locally. For longer segments, key-value pairs are gathered across devices, ensuring a constant communication cost. This approach allows for the computation of cross-attention with local queries and global key-value pairs. The algorithm's feasibility is demonstrated by scaling the sequence length while maintaining a constant latency, proving the advantage of LongNet's linear complexity and distributed capabilities. Table 2 presents the perplexity scores of language models for LongNet and several baseline models. The perplexity is evaluated across different sequence lengths ranging from 2K to 32K tokens. The results indicate that LongNet consistently achieves lower perplexity compared to the baseline models, demonstrating its superior performance in language modeling tasks. For sequence lengths longer than the model's maximum supported length, block-wise causal attention is employed to improve the model's ability to handle such inputs. This approach ensures that LongNet can effectively manage and model long sequences, which is crucial for tasks requiring extensive context understanding. In this slide, we discuss the implementation of LongNet for language modeling. The backbone architecture is based on Magneto, with a hidden dimension of 768, 12 attention heads, and 12 decoder layers. The standard attention mechanism is replaced with dilated attention. The model is pre-trained using the stack dataset, which includes source code in over 300 programming languages. The data is preprocessed with the TickToken tokenizer, and the model is trained with a batch size of 0.5 million tokens for 300,000 steps. We compare LongNet with both vanilla transformer and sparse transformers, focusing on the differences in attention layers while keeping other aspects the same. The sequence length is scaled from 2K to 32K, with the batch size adjusted to maintain a constant number of tokens per batch. Figure 6 illustrates the test perplexity of LongNet and dense transformers across various sequence lengths during training. The key observation is that LongNet consistently achieves a lower perplexity compared to dense transformers, indicating better performance in language modeling tasks. Additionally, LongNet requires significantly less computational resources, making it more efficient. This efficiency is particularly evident in the ability to scale up the sequence length more effectively, which is crucial for handling longer-range dependencies in language models. In this study, the authors investigate the scaling properties of LongNet models across a range of sizes, from 125 million to 2.7 billion parameters. The largest model was trained on 300 billion tokens, while smaller models were trained on approximately 40 billion tokens. The test loss results indicate that LongNet follows a power loss similar to that observed in vanilla transformers. This suggests that the dense transformer architecture is not a prerequisite for scaling language models. The compute required for training was estimated by calculating the total floating point operations, flops, of matrix multiplication. These findings highlight LongNet's capability to achieve both scalability and efficiency in large-scale language modeling. Figure 7 illustrates the performance of LongNet with respect to model size and context window length. On the left, the test loss of LongNet is shown as the model size increases, demonstrating a scaling curve that closely follows the pattern observed in vanilla transformers. This indicates that LongNet adheres to the same power law scaling with compute. On the right, the test loss is depicted for different context window sizes, revealing that longer context windows result in better language modeling performance. This highlights LongNet's ability to effectively leverage extended context to enhance its language modeling capabilities. In conclusion, LongNet is a transformer variant that can scale sequence lengths to up to 1 billion tokens without compromising performance on shorter sequences. The key innovation is the use of dilated attention, which reduces computational complexity from quadratic to linear. LongNet's performance has been shown to be superior to strong baselines in both long and short sequence modeling, and it supports distributed training across multiple GPU devices. Looking ahead, the authors plan to extend LongNet to support additional tasks such as multimodal large language modeling and genomic data modeling. The research acknowledges the early contributions of Xingxing and Jiayu in the exploration of the flash attention kernel. Thank you for watching.